All right, no voice. Okay, so confirm me. Is it clear now? Am I audible to all of you? Is it audible now? Are you all getting my voice? The video and audio properly? All right, thank you. Clear, now clear. All right, thank you. So, after the GPAT, it's time for NIPER. Okay, so from today, we are going to see some of the classes that will be beneficial for you all regarding the NIPER examinations. This will be a 7 classes, the 7 classes series for you all for GDC English batches that will be specifically designed for the NIPER examinations. In these classes, we are going to see the previous year questions that are asked in the NIPER examinations, the related questions with the previous year questions. So, it's the first class, the class of pharmaceutical chemistry. In today's class, we are going to see the questions from the pharmaceutical syllabus, like it. We are going to see the questions from organic. We are going to see the questions from analysis and medicinal as well. So, are you all ready? Just let me know in the comment section. Okay. Now clear. Let's start. All right, so let's start today's session. Let's have our first question. The first question, that is, which one have shortest bond length? And this was the question from the NIPER-Z 2023 examinations. So the question is, which of the following will be having the shortest bond length? There is no any specific reason or a specific question asked regarding the which bond we are going to see. Like in ethane, we can have carbon-carbon bond length, as well as we are going to have the carbon-hydrogen bonds length. So we are having carbon-carbon single bonds and carbon-hydrogen double bond, carbon-hydrogen bond. So we are having two types of bonds in the structure of ethane. In the structure of ethane, we are having carbon-carbon double bonds and a carbon-hydrogen single bond. In the case of ethane, we are having carbon-carbon triple bond and a carbon-hydrogen bond. Correct? Now, next we are having a hydrogen. Like we are going to see the bonds of a hydrogen. So as we all know, the atomic size of hydrogen is very small. So the least bond length among all the given options must be of hydrogen. So the bond length between the hydrogen in a molecule will be the least one. And yes, we are going to have the right answer from here, that it will be hydrogen. So yes, D will be the right answer for your question. And this was the question that was asked in the NIPER-Z 2023 examinations. Look, for the NIPER's demand regarding the questions are very, or you can say the very low level. There is no as such questions like you have seen in the GPAT examinations. The GPAT examinations level is too much high. GPAT is like the pre, you can say that it's a pre-examination, but the mains examination, that is for the NIPER. The NIPER examination basically it doesn't like want your knowledge. It is not about the knowledge that you are having. If you have qualified the GPAT or GATE examinations, then only you can go for the NIPER examination. So it is not about the knowledge. You already have shown that yes, you are having the knowledge in the GPAT and GATE examinations. This is all about the timing. For the 200 question, you are having only 120 minutes. So this is the totally game that is dependent on the timing. Just see the questions and answer it. All right. So moving to the next question. So we are having like, yes, for the case of carbon-carbon single bond, double bond and triple bond, the carbon-carbon triple bond will be having the least bond length. Carbon-carbon double bond will be having a little more bond length, and the carbon-carbon sigma bond, that is the case of ethane, that will be having the highest bond length, longest bond length. Okay. All right. Next question we are having, which of the following has the anti-aromatic structure? So which will be having anti-aromatic structure? Benzene. Benzene is a aromatic structure. Cyclobutadiene, so we are having cyclobutadiene, that is also known as a 4-annuline. That is also known as a 4-annuline. So yes, 4-annuline is a anti-aromatic structure. It is having 4 pi electrons. So yes, it is having 4 pi electron system, and according to Huckel's rule, if the conjugation of electrons are 4 pi electrons, it will be an anti-aromatic structure. Cyclopentadienyl anion. Look, cyclopentadienyl cation will be an anti-aromatic structure due to 4 pi electron system, while cyclopentadienyl anion is an aromatic structure due to 6 pi electron system. So yes, this is also an aromatic system. And cyclopropenyl cation, it is having a 2 pi electron system, that is a 4n plus 2 is equals to 2 electron. You will be going to see the n is equals to 0 in this case, and yes, this is also an aromatic system. So this is aromatic, this is aromatic, this is aromatic. Your question was which is anti-aromatic, so it will be B, that is cyclobutadiene. Cyclobutadiene, ठीक है ना? Done? Okay, Samaira. But look, this channel is related to the English, so just focus on this. Okay. So it will be cyclobutadiene, that is also known as 4-annuline. Next question, it is about which of the following is anti-aromatic compound, which is anti-aromatic. ठीक है? All right. Yes. All right, Vansika, you got it. Which of the following is anti-aromatic compound? Which is anti-aromatic compound? Again, the question, and this was from the NIPERS 2018 examinations. All right. So this is cyclooctatetraene. That is also known as non-aromatic structure. Why non-aromatic? It is following 8 pi electrons, and due to 8 pi electron, it must be having 4n pi electron in conjugation, that is related to the anti-aromatic compound. According to Huckel, 4n pi electrons is related to the anti-aromatic systems. But in this case, this is having non-planar symmetry, and due to non-planar symmetry, this structure is a non-aromatic compound. Again, we are having 4-annuline, that is an anti-aromatic system. We are having cyclopentadienyl anion, that is aromatic. And this is pyrrole, so this is aromatic, this one is also aromatic, this is non-aromatic, and this is anti-aromatic. So yes, your question was regarding aromatic anti. So yes, B will be the right answer, that is B is an anti-aromatic structure. Okay, all right. Oh ho. All right, this is going to be very funny class, I guess, due to tough safe geometry. All right. So which of the following correctly represents order of carbon-carbon bond length from longest to shortest? Again, we are having the same question regarding the concept that we have studied in the first question, that is the longest and the shortest bond length. So we are having alkanes, that is having carbon-carbon single bonds. For the case of alkene, that is having carbon-carbon double bond, and for the cases of alkynes, we are seeing that carbon-carbon will be having a triple bond. So bond order of alkynes will be 3. Bond order for the alkenes will be having 2, and for bond order for alkanes it will be 1. Greater the bond order, shorter the bond length of that particular compound will be. So for the case of here, like alkane will be having the highest bond length, longest bond length. Next we will be having alkene, so no, this is incorrect, alkane, then followed by alkene and alkyne. So yes, C is the right answer. C will be the right answer for this question. Alright, C is the right answer. Yes. Moving ahead with the next question, we are having which of the following is more stable intermediate carbocation in pinacol rearrangement? So pinacol rearrangement, we are having pinacol rearrangement. Pinacol rearrangement is a name reaction, that is like this is related to the compounds of ketones. When acetone is treated with MgHg, we are going to see an pinacol. Basically, we are having C double bond, CH3 and CH3. The 2 moles of acetone in MgHg is converted into CH3, 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 OH, OH. This is also known as vicinal diol. That is when the OH group are present at 1,2 positions, adjacent carbons. This is a vicinal position. and when the OH groups, two OH group are present on the same carbon, that is also known as geminal diols. So this is pinacol, and after the dehydration, it is converted into, or it is rearranged into the pinacolone, and the carbocation intermediate is formed here, and the carbocation, that is after the shifting, after the rearrangement, we are going to see the question that like a carbocation that is having a tertiary carbocation, the more stable carbocation, that is 3-degree carbocation, 3-degree carbocation. So yes, C is the right answer. Then C is the right answer. Yes, after the dehydration, it will be a 3-degree carbocation is seen. 3-degree carbocation in presence of MgHg and after dehydration. Yes, very right, very right. Naphthalene undergoes oxidation with KMnO4 H2SO4. We are having a naphthalene structure, and this naphthalene basically when reacts with the KMnO4, that is potassium permanganate, and is also a stronger oxidizing agent in presence of H2SO4, the reactivity of this KMnO4 with this naphthalene for the oxidation increases due to this presence of H2SO4. So this basically converts the structure into COOH, COOH, that is also known as a phthalic acid. That is also known as a phthalic acid, phthalic acid. And when we take like V2O5 in the presence of this KMnO4 and H2SO4, the naphthalene is converted into phthalic anhydride. So the right answer for this question, that will be phthalic acid. Basically, this naphthalene gets converted into phthalic acid with the help of KNO4 and H2SO4. So yes, C is the right answer. C is the correct answer for this question. C is the right answer. Okay, sir, will we study only chemistry today, or will we revise today's model paper here? Vanshika, in this class, we are going to see only the 100 questions regarding your NIPER examinations. No model paper. For the model paper, it will be conducted on the 9 o'clock on the main channel, that is GPAT Discussion Center official YouTube channel of the Hindi batch. All right. So here we are going to see only 100 questions from the pharmaceutical chemistry. It will be no relation with the model papers. Which one of the following structure is optically active? Which is optically active? Like 1,3-dichloroalkene? Not at all. Not at all possible for the case of alkenes. Biphenyl, ortho-substituted biphenyl, so heteroisomerism, that is related to the optical activity of the compound. So yes, biphenyls can show the optical isomerism. Mesotartaric acid, this will be not having any kind of optical activity. No optical activity. Like a 2-chloro-2-methylpropane, this structure is also having no chiral carbon, so no optical activity is possible in this structure as well. So no optical activity on these A, C and D. Yes, but B, the bulkier group substitutions at the ortho position of the biphenyls can show heteroisomerism, that is related to the, after the rotation around a single bond, it can have a optical activity, the mirror image relationships. So yes, this biphenyl system can show the optical activities. Biphenyl system, if we substitute these ortho positions with some bulky groups like iodine, NO2, carboxylic or other bulkier groups. Which of the following product is formed in a Reimer-Tiemann reaction? So in the case of Reimer-Tiemann reaction, we are basically having a phenol that is treated with the CHCl3 and NaOH, and in this we see there is a formation of ortho substituted phenol, and this is like the benzaldehyde having OH on the ortho position, that is OH group on the ortho position, that is also known as salicylaldehyde, So yes, this D will be the right answer. Rotation around a single bond is hindered. No. Rotation around single bond is possible. There is no restricted rotation around that particular single bond in the biphenyls. Virat, the restricted rotation is possible only in the cyclic structures, the cycloalkanes, where geometrical isomerism can be seen. But for the cases of biphenyls, there is no such restricted rotation. The single bond have free rotations. Okay, that is why it is known as heteroisomerism. All right, so yes, D will be the right answer. D will be the right answer. Done? Okay. Next question we are having, compounds which are mirror images of each other are not superimposable. Like they are mirror images of each other and with each other and not superimposable. So non-superimposable mirror images are also known as enantiomers. They are basically optically active compounds. They are optically active compounds, so they are known as enantiomers. Non-superimposable mirror images are also known as enantiomers. So yes, A is the right answer for this question. Enantiomers. Reagents used in the benzoin condensation. So for the benzoin condensation, we are going to see an nucleophilic reagent like KCN. It is having K plus and Cn minus. So yes, we are having a nucleophilic reagent. No, it's a reducing agent. Like this reagent is used in the Clemmensen reduction reaction. So we are going to use like KCN and ethyl alcohol. So yes, B is the right answer for this question. Like in the case of benzoin condensation, we are going to see like when KCN and ethyl alcohol are used. For the next question, we are having 𝘂𝙧𝙎𝙏 rule, that is a CIP rule. That is a CIP rule. So for the CIP rule, what is the correct option in the mentioned? Nomenclature of stereoisomers. This CIP is used for the nomenclature of stereoisomers. Yes. This CIP rule, that is 𝘂𝙧𝙎𝙏 sequence rule, is used for the determination of the E and Z, that is end Z and Zusammen projections for the geometrical isomers, as well as it is used for the nomenclature of the R and S systems, that is rectus sinister system, for the case of optical activity. That is also a kind of absolute configuration. Absolute configurations. So yes, this nomenclature of stereoisomerism, it can be only possible due to the 𝘂𝙧𝙎𝙏 sequence rule, that is also sometimes known as priority sequence rule. So yes, A is the right answer for this question. A will be the right answer for this question. Vilsmeier-Haack reaction gives, like Vilsmeier-Haack reaction in the presence of THF when we use POCl3. What we are going to get? We are going to see like a carbonyl group basically added to the aromatic system in a electrophilic substitution mechanism. And this reaction is basically used to introduce the formyl groups. In general, a formyl group or a substituted, like, or it could be a ketone group as well. So it's not for the amide, not for the amine, not for just nitrates. It could be a ketone. Basically, it's a carbonyl groups, and most preferably it is a formyl group, that is HCHO. Means a CHO group basically gets added to the aromatic ring system. So yes, it's a ketone. It could be a correct answer, since during the NIPER examination this question was asked and there was no such option regarding the formyl group. So yes, it could be a ketone. C can be the right answer. Vilsmeier-Haack reaction. This reaction mechanism is favored by substrate low temperature, like substrate low temperatures. All right, so low temperature and substrate, done. Polar solvent, okay, and a concentration of nucleophile. So the concentration of nucleophile in a lower temperature and substrate. So basically, when the rate of reaction is depending on the substrate as well as on the concentration of your nucleophile. In a polar solvent. So this basically gives the idea, like, yes, this reaction will be a SN2 reaction. It just be a SN2 reaction. In the case of SN1 reaction, there is no such requirement for the nature of nucleophile. No dependency for the rate of reaction on the concentration of your nucleophile. That's why they are unimolecular reaction, while this reaction is a bimolecular reaction where the rate of reaction depends on the concentration of substrates as well as on the concentration of your nucleophiles. Okay, so yes, D is the right answer. D will be the right answer. Like next question we are having, select the correct statement for phenanthrene. It's a question from the NIPER 2018 examination. Like phenanthrene is also known as polycyclic aromatic compounds. They are basically constituting 3 benzene ring system. They are comprised of 3 benzene ring system, and they are basically having a non-linear symmetry. They are having non-linear fusion of these 3 benzene rings. They are isomer of the anthracene. Phenanthrene is an isomeric structure with the anthracene, like phenanthrene. So polycyclic aromatic carbon, okay, it's the correct one. Heterocyclic, no. Phenanthrene do not have any kind of heteroatom on their rings, so it could never be a heterocyclic. It's a polycyclic non-aromatic, no, not at all. 3 benzene ring make it structure as a aromatic system. Heterocyclic, not at all possible. So yes, just A is the right answer. Like it's a polycyclic aromatic hydrocarbon. Okay, A will be the right answer. Mechanism of SN2 involves. So the case of SN2. In the case of SN2, there is substitution of your alkyl halide in general, and the alkyl halide get converted into alcohol. We are having a transition state. In the transition state, the carbon that is having your leaving group attached will be having a pentavalency. That particular carbon that is constituting the leaving group will be having a pentavalency, the 5 bonds for in its transition state. So we are having formation of a racemic mixture, not at all possible. With respect to the racemic or racemization or inversion, the SN2 reactions just only have inversion in configuration. There is no case for the retention in configuration, since the nucleophile can only attack to that particular substrate reagent in a backward direction. There is no such case like, yes, your nucleophile can attack from the direction from which your leaving group is going to be removed. There is no such possibilities. So it's only having 100% inverted in configurations. So yes, B is the right answer. Like yes, for the SN2, there is only inversion in configuration that can be seen. For the case of SN1, there can be inversion as well as retention. So yes, there is formation of a racemic mixture, you can say. So for the case of SN2, it will be just B as your right answer. B will be your right answer. B is your correct answer. Umbrella shaped, yeah, very right, very, yes, umbrella shaped, that is also known as Walden inversion. And this 100% inversion, that is also known as Walden inversion. Inversion in configuration is also termed as Walden inversion. Okay. Next question we are having. The hybridization state of a carbocation is. Hybridization state of a carbocation. So for the case of carbocation, we are having sp hybridization, sp3 hybridization, sp2 and sp3d. So carbocation that is having a planar geometry, and we are having sp2 hybridization state. We will be having sp2 hybridization state. So C will be the right answer. C will be the right answer. C is the correct answer. Anti-aromatic compound from the given structure, anti-aromatic compound, cyclopentadienyl cation. Yes, this cyclopentadienyl cation, it's an anti-aromatic system. Like it will be having just 4n pi electron systems. 4n pi electron system. Cyclopentadienyl anion will be having 6 pi electron system, aromatic, phenyl aromatic, naphthyl aromatic. But this cyclopentadienyl cation will be an anti-aromatic structure, anti-aromatic compound, and this was the question from the NIPERS A 2099. So A will be the right answer. Nitro group is an electron withdrawing group. It directs the incoming group to the following position of the electrophilic substitution reaction. For the case of benzene, we are having a nitro group attached to this benzene system. Let's suppose we are having a nitro group. This nitro group is a electron withdrawing group. It already mentioned here. So this nitro group will be having electron deficiencies on the ortho and para positions. And yes, at the ortho position and para position, since it's decreasing the electron density and the electrophile is already having a positive electron center. It's already an electron deficient center. So the possibility for this electrophile to attract or towards this benzene ring is possible only at the meta positions with respect to this nitro group. So yes, it's only a meta directing group. It's a meta directing group. D will be the right answer. D will be the right answer. D is the correct answer. Hybridization of methane. For the hybridization of methane, we are having 2 p orbitals, 2 s orbital, not at all possible. It's only 1 s orbital that can have participation for the hybridization. 3 p orbitals and 2 s orbitals. 3 s orbitals, not at all possible. It's only because of 3 p orbitals are involved in such hybridization in methane. So yes, C will be your right answer. NBS, that is N-bromosuccinimide, catalyzes the what type of reaction? The N-bromosuccinimide, that is known as NBS. So this NBS basically having Aromatic nucleophilic substitution reactions, aromatic electrophilic substitution reaction. Yes, this NBS basically gives a bromine, bromonium ion, and this bromonium can attack the benzene ring that can show the electrophilic aromatic substitution reaction, the bromination of benzene. So yes, it's a case about the electrophilic substitution reaction of bromine inside the benzene ring. So B is your right answer. B is your right answer. Which type of configuration present in R and S system? So for the case of R and S system, what kind of configurations are there? What kind of configurations are there? Absolute, relative, conformational, or optical? So yes, which will be the right answer? It's absolute configurations. R and S are absolute configurations. Alright, R and S are absolute configurations. Okay, A is the right answer. Which of the following is not a heteroaromatic? Which will be not a heteroaromatic compound? Heteroaromatic. Azulene is not a heteroaromatic compound. Azulene is having basically a 7 and a 5 member benzene ring system attached. So 7 and 5 member. 7 and 5 member rings. It's a 7 member and it's a 5 member ring attached. It's a homocyclic, it's not a heterocyclic ring. Pyridine is having a 6 member nitrogen containing heterocyclic ring, 2 nitrogen atoms on a 6 member ring, 5 member ring with single nitrogen. These all are heteroaromatic. While this is not a heteroaromatic. Azulene is not a heteroaromatic compound. Okay, so yes, A will be the correct answer. Intermediate in the aldol condensation reaction. The question from the NIPER 2021. Intermediate in the aldol condensation. Since aldol condensation follows the 𝐸1𝐶𝐵 mechanism, it will be having a carbanionic intermediate. Carbanionic intermediate, which is basically alpha containing carbonyl compounds. So these kind of reactions, and the end product of this reaction is alpha beta unsaturated carbonyl, alpha beta unsaturated keto compounds. So we are having a intermediate, that is enolate ion. Enolate ion. It's a carbanionic intermediate. So enolate ion will be the right answer. B is the correct answer for this question. 𝐸1𝐶𝐵 mechanism followed in these kind of reaction mechanisms. Which of the following reactions is not shown by alkenes? Pyrolysis reaction. Pyrolysis is the breaking of a chain into simpler, smaller segments. So yes, pyrolysis is possible, aromatization is possible, addition reaction is very, very possible in the alkenes, while the substitution, this substitution is possible in the cases of alkanes or sp3 hybridized carbons. sp3 hybridized carbons, while the alkenes are having basically sp2 hybridizations. So yes, alkenes do not show substitution kind of reactions, but these reactions can be shown by alkenes very frequently. So yes, D is the right answer. D will be the correct answer regarding this question. Okay, D will be the right answer. Shivani, you have joined the GPAT English. You are watching me on the GPAT English channel. Okay. Moving to the next question. Which of the following is not aromatic? Which is not aromatic? Thiophene, dioxane, pyrrole, or isoxazole? Isoxazole is the 5-member heterocyclic ring that is having the oxygen and nitrogen on the 1,2 position. If they are present on the 1,3 position, it will be oxazole. While isoxazole, that is isomer of oxazole, it means that oxygen and nitrogen are present at the 1,2 positions. Okay, so it's a aromatic ring. All right. Pyrrole, it's a aromatic ring with 5-member. Dioxane, so dioxane basically do not have any conjugated ring system. It's a 6-member ring in which the oxygen could be present at the 1,2 or 1,3 or 1,4 positions without any unsaturations. So due to absence of conjugation, non-planar geometry, this dioxane can never show aromatic structures. Thiophene is a aromatic ring. All right, thiophene is a aromatic ring. So B is the right answer. B will be the right answer. Like dioxane will never have aromatic systems. Price the rearrangement reaction of phenol esters leads to the formation of which type of product? We are having phenol esters. All right. So in presence of AlCl3, this breaks, this group breaks from this position, the OC bond, and basically this carbon with the carbotine attaches with this ring on ortho or para position. Ortho or para position. The possibilities for the ortho and para position attack is both. Done. So, what are the product that you are going to see in this? So, alkene, no, not at all possible. Aldehyde, no. Alcohol, no. It will be ketone. Like, look, we are having a ketone since it's already written. We are having a phenol ester. So, phenol is already mentioned here. So, what? Phenol is already mentioned. What is the product? That is a ketone product. Ketone product. So, yes, D, that is ketone, will be the right answer. Ketone will be the right answer. Which of the following has the highest acidic value? Reimer-Tiemann 2009. Nitrobenzoic acid, toluene benzoic acid, and aminobenzoic acid. Here we are having NH2, that is amino, and this is a plus M group that tends to decrease the acidic character of the benzoic acid. Benzoic acid is not having any kind of substitutions on the benzoic ring system. Toluene is not at all acidic. There is no any acidic hydrogen present on the structure of toluene. While this nitrobenzoic acid is having a nitro group, that is NO2 group, and this NO2 group is a minus M group, and acidity depends on the minus M. Acidic character is directly proportional to minus M, minus I nature, while inversely proportional to plus M and plus I natures. So yes, minus M or minus I, that is this A, that is nitrobenzoic acid, will be having the highest acidic strength, the highest acidic value. Alright, so A is the right answer for this question. Moving to the next question, we are having conversion of acyl azides to isocyanate reaction is known as. So we are having acyl azides. Acyl azides, azide that is having the N3. Like acyl group attached with the N3. CH3, C double bond O, N3. This is like acyl azide. When this acyl azide gets converted to isocyanate, the reaction will be, it will be Curtius rearrangement, Claisen rearrangement, Reimer-Tiemann reaction, Hofmann-Bromide degradation reaction. It will be a Curtius rearrangement reaction. It's Curtius rearrangement reaction. A is the right answer. In the Curtius rearrangement reaction, we are going to see like this acyl azide gets converted into isocyanate. Isocyanate. So yes, A will be the right answer. A will be the right answer. This is your acyl azide, and in acyl azide we are having CH3. Acyl azide. Cycloaddition is seen in the following reaction. Cycloaddition, Diels-Alder reaction, Cannizzaro reaction, aldol condensation reaction, Perkin reaction. These all are the reaction that is related to the carbonyl compounds. This Diels-Alder reaction, that is also known as cycloaddition reaction. It's the pericyclic class of reaction in which we are having a dienophile like adding with the conjugated diene system, either in the thermal or photochemical conditions, and this is the case for the cycloaddition. And it's also the question for in this year only GPAT 2025 examination, the Diels-Alder reaction belongs to what category of reaction? It's a cycloaddition reaction in a pericyclic reactions. A will be the right answer for this question. Alright, A will be the right answer. Which have sp2 hybridizations? Ethane will be having sp3 hybridizations, both the carbons are having sp3 hybridizations, just single bonds. Ethene will be having sp2 hybridizations. Ethyne will be having sp hybridizations. Methane, this is methane, that is also having a sp3 hybridizations. So the sp2 belongs to the case of alkenes, that is having ethene. So yes, B is the correct answer. B will be the correct answer. B will be the correct answer. Which one of the following statements correct for open or oxidation? So there are two reactions. One of them is MPV, that is Meerwein-Pondorf-Verley reduction reaction. In this reaction, basically a carbonyl compound, that is a ketone compound, gets reduced to secondary alcohols in the presence of aluminum isoalkoxides compounds as a catalyst. And when this same reaction is reversed, that is known as open or oxidation. It means when a 2-degree alcohol gets oxidized with the help of aluminum isoalkoxide into ketone, that is known as open or oxidation. Both the reactions MPV and open or are just reversible of each other. So it will be like conversion of oxidation of primary and secondary alcohols, not at all possible. Conversion of ketones to secondary alcohol, that is related to the MPV. It is a reduction reaction. MPV reductions. and this reaction is possible only in the presence of iso-alkoxides. Iso-alkoxides as a catalyst. Aluminum iso-alkoxides. All right, aluminum iso-alkoxides. Primary alcohol to aldehyde and ketone, not at all possible. Conversion of a secondary alcohol to ketone. Yes, this is all about open or oxidation. So yes, D is the right answer. D will be the right answer. D will be the right answer. The change in optical rotation representing conversion from alpha form to beta form is called as. So alpha form, beta form, they belongs to the glucopyranose structures. This glucopyranose structures basically show mutarotations, the cyclic form of glucose, that is also known as glucopyranose structures. This basically gets converted into alpha and beta forms, and this rotation, that is also known as mutarotation. So yes, this is a mutarotation, not mutation, no mutagenesis, it's a mutarotation. Conversion of alpha and beta forms of glucopyranose is possible only because of this mutarotation. So yes, C is the right answer. C will be the right answer. The OH when present on the OH when present just after the oxygen is on the lower side, that will be alpha, and when the OH on the first carbon after the OH is present on the upward direction, that will be a beta form of your glucose. Beta glucopyranose, alpha glucopyranose, and this is the structure of glucose, that is the cyclic structure, Fischer structure. Which of the following is aromatic? Which is aromatic? There is no conjugation present on these positions, so this is non-aromatic, this is non-aromatic. All right, this is non-aromatic while this is aromatic. Why? We are having 1, 2, 3, 4, 5, 6. We are having 6 pi electron system, complete conjugation. It's cycloheptatrinyl cation, also known as a tropylium. Tropylium is the most stable carbocation among the carbocations. So yes, C is the right answer. C will be the right answer. Which one of the following is a non-aromatic compound? This is benzene, toluene, aromatic. It's non-aromatic due to tub-shaped geometry. This will be having a tub-shaped geometry. All right, so due to tub-shaped geometry, this is non-aromatic. Aromatic pyrrole system, naphthalene also aromatic. So all three are having aromatic, while this B is having non-planar geometry. Non-planar geometry. That's why it will be a non-aromatic structure. Stereoisomers of glucose are called. So the stereoisomers of glucose, that is also known as epimer, anomer, diastereomers or enantiomers. Glucose epimers, glucose isomers, glucose stereoisomers. So basically glucose is having two kinds of stereoisomers, that is alpha form and the beta form. And this alpha and beta forms are anomers. We have just seen, like if the OH group after the oxygen is present on the downward side, that will be alpha anomer form of your glucose, alpha anomeric form, while when the OH is present on the upward direction of your carbon just after the oxygen, that will be the beta form, and the stereoisomers of glucose, that is also known as anomers. They will be known as anomers. So yes, B will be the correct answer. B will be the correct answer. Yes, B is the correct right answer. Identify the name reaction. We are having phenol when reacts with CH-Cl3 chloroform. NaOH, we are having salicylaldehyde, that is known as a Reimer-Tiemann reaction. A is the correct answer. A is the right answer for this question. Lindlar catalyst. Lindlar catalyst. So two, we are having a palladium either present with calcium carbonate or palladium when present with barium sulfate. They are also termed as Lindlar catalyst. These Lindlar catalysts are having various kind of reactions. They show various kind of reactions. So platinum, not at all possible. Chromic acid, no. Nitric acid, no. We are having palladium. So when it gets combined with the calcium carbonate, or when PD is having BaSO4. So either this or PdCaCO3. This, they are having just Lindlar catalyst composition. So yes, B is the correct answer. B will be having the correct answer. Which of the following alkyl halide will undergo SN1 reaction most readily? So which will be having alkyl halide? Which alkyl halide will be undergoing SN1? Basically SN1 is having the best carbocation, that is 3 degree tertiary carbocation. The better stabilized carbocation, the more faster it gets converted into that particular carbocation intermediate. we are having like all the compounds, all the structures are having same kind of intermediate formation, that is having tertiary carbocation. So the reaction now depends only and only on the leaving group. Among them, like we are having iodine, bromine, chlorine and fluorine. The higher bond length is present on the iodine carbon, that is having the better leaving group, iodide ion. The best leaving group among all these will be iodide. So yes, D is the correct answer. D will be the correct answer. Iodide due to better leaving group. Iodide due to better leaving group will be having the fastest SN1 reaction. Which is correct about aromatic compounds? Which will be correct about the aromatic compounds? Aromatic compounds. These are following Huckel's rule. These are cyclic compounds. These are having localized pi electrons. Look, localized, not at all possible. The aromatic compounds must have delocalized electron pairs. So this is wrong. Never all of the above can be right answer among this. These are cyclic. Yes, they could be cyclic, but this is not just the 100% true criteria. Like many of the cyclic structures are not aromatic. So yes, it would be not the appropriate answer. The correct appropriate answer now will be having just A. That is, these are following Huckel's rule. These are following Huckel's rule. A will be the right answer. A will be the correct answer. Next we are having the catalyst used in the Clemmensen reduction. So for the Clemmensen reduction reactions, we are having like when the carbonyl compound gets reduced to the respected hydrocarbons in the presence of zinc amalgam and HCl. Zinc amalgam and HCl, lithium aluminum hydride is the strongest reducing agent. It can reduce carboxylic acids, esters to their respective alcohols. H2PT, this is about the double bonded carbon system. They basically reduce the double bonded carbon systems, triple bonded carbon systems. KOH is a base, while this zinc amalgam HCl, yes, this zinc amalgam and HCl is a reagent that is used by the carbonyl compounds to reduce them into their respected hydrocarbons. So yes, this is about the Clemmensen reduction reactions. D will be the right answer. And NH2NH2 in presence of base is used for the Wolff-Kishner reduction. Very good, Siddha. Moving to the next question, we are having racemic products are formed in the reaction. So the racemic products can be seen in which kind of reactions? Racemic products, SN1, SN2, SNI or E1. So the SN1 can have, due to carbocation intermediate, due to planar geometry of your intermediate, it could be having retentions as well as inversions. Retention as well as inversion. Retention, inversion. So both of them are possible. So that's why the SN1 can only have the possibility for the racemic products. Your product ultimately will be having racemic products, while this SN2 will be having just 100% inversion. 100% inversion, that is also known as Walden inversion. So yes, B is for inverted product, A is for the racemic product. So yes, A will be your right answer for the question. Which of the following compounds are anti-aromatic? Like we are having furane and there is no any charge present for the conjugation. So this is aromatic system, while this is non-aromatic system. This is non-aromatic, cycloocta, tetraene. Furane is an aromatic system. Here we are having cyclopentadienyl cation. So due to 4 pi electron system, it's an anti-aromatic. It's an anti-aromatic structure. 4-aniline is also an anti-aromatic system. So yes, fifth and sixth, B will be your right answer. B is the correct answer. B will be the right answer. Electrophilic substitution reaction of indole occurs at. So for the case of indole basically having benzene ring fused with the pyrrole. Benzene ring fused with the pyrrole system. So this third position is having reactions for the electrophilic substitution reaction for the case of indole. This 3 position is related to the indole. This is for indole. This fourth is for the fourth position will be possible. Second position is possible for the pyrrole, furane and thiophenes. Fifth position is possible for the quinoline and isoquinoline. Now tell me, the fourth position electrophilic substitution reaction at the fourth position is possible in what kind of compounds? I can give you a hint, like it's a 5-member ring with 2 heteroatoms. So for the indole, it will be A, that is 3, third position. So you can see like bromination, sulfonation, like we are having nitration or Mannich reaction, Vilsmeier-Haack reaction, Reimer-Tiemann reaction, all of these are possible at the third position. Caprolactam is synthesized from the question from 𝘖𝙂𝙎 2021 examinations. Yes, it's for the pyrazole, oxazole, imidazole, all those 5-member ring system that are having 2 heteroatoms attached. It will be having 4th and 5th position for the ESR, 4th and 5th for the electrophilic substitution reactions. Now, this caprolactam ring, that is also known as cyclic amide. Now, this cyclic amide is possible only when we rearrange the oxime into amide, and the conversion of this oxime into amide, that is also known as caprolactam, is possible because of the Beckmann rearrangement. When we are rearranging the oxime, ketoxime, in the presence of an acid into caprolactam, into amide, the formation of this caprolactam, the cyclic amide is seen, and this is related to the Beckmann rearrangement. This is all related to the Beckmann rearrangement. Solvent used in SN1 reaction. So for the SN1 reaction, we are having a polar as well as a protic solvent. The polar that are having a polarity, and the protic, that is the solvent that are having tendency to donate H+ ions, protons. So they are protic solvents. So yes, all the like water, methanol, they all are having polar as well as protic solvents. So yes, polar, protic, so both. So C is the right answer. And for the case of SN2, we are having like solvents will be having polar and aprotic. Polar aprotic solvent. Aprotic solvent that are not having a tendency to donate proton. They are polar but they are not protic. That is like THF, tetrahydrofuran. DMF, dimethyl formide. DMF. DMSO, dimethyl sulfoxide. Acetone, simplest form, acetone, that is also a polar aprotic solvent. So these kind of solvents are used for the SN2 reactions, polar aprotic, but for SN1 we are having polar and protic solvents. Next question, we are having 𝘿𝙄𝙎𝙎𝙄𝙊 reaction is catalyzed, like a reaction catalyst. What is the catalyst that is used for the 𝘿𝙄𝙎𝙎𝙎𝙄? The question from the 𝘖𝙂𝙎 2023 examination. HVZ reaction, HVZ, 𝘿𝙄𝙎𝙎𝙎𝙄, that is alpha halogenation of carboxylic acid. And this alpha halogenation of carboxylic acid is possible only when a carboxylic acid that is having alpha hydrogens is treated with halogen in presence of red phosphorus. So all the alpha hydrogens of that particular acid gets substituted with that respected halogen, So it's zinc amalgam, no. It's NiPT, no. It's yes. It's the red phosphorus. It will be red phosphorus that we are going to use for this kind of reaction. It's for the halogenation of alpha hydrogens in a carboxylic acid. Okay. So the carboxylic acid with alpha hydrogens. We are having 3 alpha hydrogens in acetic acid. One by one, you can see like yes, there is substitution with the 1 hydrogen, 2 substitutions and 3 substitutions. This is possible only because of red phosphorus when treated with the halogens. Feist-Benary synthesis is related to that. So Feist-Benary synthesis. This is all about the synthesis reaction of furan. So this Feist-Benary reaction is related to the furan. The synthesis of furan is possible because of Feist and Benary synthesis reaction. Stability order of conjugated, isolated and cumulative dienes. The question from the 𝘖𝙂𝙎 2019. Alright, so the conjugated, that is having conjugation, the alternate positions of the double bond. Isolated, that is no any relation with the double bonds, the 2 double bonds that are not having any kind of relations, like it could be very far from each other. And cumulative, that are just adjacent positions of the pi bonds, the 2 pi bonds that are just adjacent to each other. So the stability is that like this conjugated alkene will be having the highest stability, followed by the isolated one. The cumulative alkenes, that is also known as alene, it will like this alene system will be having the least stability due to consecutive pi bond formations. So yes, the stability will be conjugated, but after the conjugation it will be isolated. So conjugated, then isolated, then cumulated. Though stability is conjugated followed by isolated and the cumulative ones. HVZ reaction involves only alpha halogenation of aliphatic carboxylic acid in the presence of a small amount of, again the question from the Reimer-Tiemann 2021. It's nitrogen, sulfur, peroxide, no, it's red phosphorus. So yes, B is the correct answer. B is the correct answer, red phosphorus. Halogen exchange reaction is halogen exchange, Mendius reaction, Curtius reaction, Schwarz reaction. Alright, so this Schwarz and Gattermann. Alright. This Schwarz reaction is about the formation of alkyl fluorides and we are having halogen exchange. So basically when we are having one of the haloalkanes, if this haloalkanes is reacted with AgF, this halogen, it could be any fluorine or chlorine. So this halogen gets substituted with the respective fluorine and the formation of fluoroalkane is possible. Fluoroalkane is possible. So it's a halogen exchange reaction that is Schwarz reaction. That is also known as Schwarz reaction. So yes, C is the right answer for this question. How many chiral stereoisomers can be drawn for CH3, CHCl, CHBr, CH3? All right. Oh, okay. So answer is already mentioned here. We are having CH3, CH, Cl, CHBr and CH3. Since we are not having any kind of symmetry, we do not have any kind of symmetry present here. So the possibility of the meso form of this structure is never possible. That's why we are having two chiral centers and absence of symmetry. So we are having 2 to the power 2 and we are having 4 isomers. So yes, C is the correct answer. C will be the right answer for this question. C is the right answer. Like yes, it will be having a 2 forms. 2 chiral carbon and 4 stereoisomers can be drawn for this question. Choose the number of stereoisomers of tartaric acid. All right. So the tartaric acid will be having carboxylic, OH, H, OH, H. There is possibility of plane of symmetry. So we are having 2 chiral carbon systems, 2 chiral carbons. So we can have 3 stereoisomers that can be drawn for this tartaric acid structure. It never be 1, it's not 2, it's not 4, it's 3. One of them could be this one, the other will be this one, OH, H, OH, H and COOH, and the other one will be the mirror image of this structure, right? OH, H, H, OH, COOH. So we are having 1 form, 2 form and 3 form. This is known as mesotartaric acid, that is optically inactive. Optically inactive, while the other 2 isomers are optically active enantiomers of tartaric acid. So yes, C, that is 3 will be the right answer for this question. Wittig reaction is used for Reimer-Tiemann 2021. Wittig reaction. When we treat carbonyl compound with triphenylphosphines, that is also known as 𝘖𝙬. So after the betaine intermediate, we can see that alkene is formed. Formation of an alkene can be seen. So it's the reaction that is related to the conversion of aldehydes into alkenes. Aldehyde to alkene, yes, correct. Alkene to aldehyde, no. Alkene like aldehyde to alkane, not at all possible. Not at all possible. It's the reaction of triphenylphosphines, triphenylphosphorus alkenes with a aldehyde, that is conversion into the alkene. So yes, A is the correct answer. A will be the right answer. This is also known as triphenylphosphine, also known as 𝘖𝙬. Okay. Geometrical isomerism is possible in, so GI is possible in acetone-oxime, isobutene, acetophenone-oxime or benzophenone-oxime. Geometrical isomerism is possible only on the structure that are having restricted rotation, that is presence of a pi bond, and both the atoms that are having restricted rotations must be having two different groups attached on a single atom. Acetone oxime, that is having like this one, CH3, double bond, acetone oxime, NOH. This restricted carbon will be having both the same groups, CH3. Isobutene will be having H, this one. So this restricted atom is having same groups. Next, acetophenone oxime, all right. So this can be correct one, acetophenone. We are having aceto and phenone, NOH lone pairs. Carbon with double bond on hydrogen is having CH3 and phenyl groups. All right, so both the groups are different, OH and HES. It's having syn and anti kind of geometrical isomerism, or it can also have a EZ system of nomenclature. Benzophenone, both the benzene rings are present, not at all possible, like benzene here and NOH. So again, this is not possible. So C is the right answer, that is acetophenone oxime will be the correct. Acetophenone will be the correct answer for this question. All right, moving to the next question, we are having the organic reaction of primary amide to primary amine with fewer carbon atoms is known as. Organic reaction of primary amide into primary amine with fewer carbon, that is loss of carbon is taking place. It could be possible only when the amide gets treated with the bromine in 𝘂𝙬𝙎, that is also known as Hofmann bromide degradation reaction. And there is always a formation of primary amine, that is 1 degree amine is possible. It's the reaction of Hofmann bromamide degradation reaction, that is also known as Hofmann rearrangement. So D will be the right answer. There is an explanation about the Baeyer Villiger. All right, so it's like Hofmann bromide degradation reaction. When the amide gets treated with the Br2 and 𝘂𝙬𝙎, it gets converted into 1 degree amine. Quinoline shows the reaction, like quinoline will be having nucleophilic addition reactions, nucleophilic substitution reactions, electrophilic aromatic addition reactions, electrophilic substitution reactions. All right, so the quinoline is an aromatic compound, and the aromatic compound shows substitution kind of reaction, so there is no possibility for the addition reactions. The majority of reactions, it could be having a nucleophilic substitutions as well. There is possibility for the nucleophilic substitutions as well, but the nucleophilic substitution is possible only at the C2 position, only at the C2 positions, and this is not that much seen. But this electrophilic substitution, it could be having many kind of electrophilic substitution reaction possible on the quinoline structures. So yes, the majority or the appropriate answer for this question will be, it will be like electrophilic substitution reaction. D will be the correct answer. Next question, we are having stereoisomers which are not mirror images of each other are called. So the stereoisomers that do not belong to the mirror images, since they are not mirror images of each other, they will be different images, and the different images are known as dia-stereoisomers. DIA, that is different images are dia-stereoisomers. So the isomers, the stereoisomers that are not mirror image of each other, that are not related to as mirror images, they are dia-stereoisomers, and the dia-stereoisomers are having different physical properties. All the geometrical isomerism will be having dia-stereoisomers or dia-stereoisomers. So yes, A is the right answer. The correct order of acidic strength of the given acids is, we are having formic acid, acetic acid, and propanoic acid. So for the case of formic acid, we are having HCOOH. For the case of acetic acid, we are having CH3COOH. And for the propanoic acid, we are having CH3CH2COOH. Again, we are having plus I nature, no any group. The acidic character gets decreased with the increasing plus I natures. Here we will be having the greater plus I strength, little less plus I strength, while this will be having no plus I nature. So acetic acid will be more acidic, more acidic than propanoic, and formic acid is more acidic than the acetic acid. So the correct answer, for this question will be formic, most acidic, followed by acetic, and propanoic. All right, so A will be the correct answer. A will be the right answer. Which conformer of cyclohexane is chiral? Which conformer of cyclohexane is chiral? So the conformations of cyclohexane is 4, like chair form, boat form, twist boat, and half chair. So the chiral conformer of cyclohexane is twist boat. That is also known as twisted boat. So yes, C, that is twist boat. This basically will be having the chiral conformations. Chiral conformation. The twist boat conformation is having chiral conformation. The addition of HCN to carbonyl compound. We are having a carbonyl compound. So when we get HCN reacted with this carbonyl compound, this is basically H plus and Cn minus. H plus and Cn minus. This Cn minus attracts to this carbonyl carbon that is having electron deficiency. So this is a case for the nucleophilic addition reactions. This HCN or the Grignard reagent gets added to the carbonyl compound, and these kind of reactions is known as nucleophilic addition reaction. Nucleophilic addition reaction. C will be the correct answer. C is the right answer. Which of the following shows linear structure? Which will be having the linear structure? Ethane, ethene, acetylene, or CCl4? Linear structure that is having the sp hybridization. Since the sp hybridization is having 180-degree bond angle, and the symmetry of this particular structure will be linear. Ethane is having sp3 hybridization, so this structure will be having tetrahedral symmetry. Tetrahedral symmetry. All right. The ethene is having sp2 hybridizations, so the symmetry is planar. Planar symmetry. Acetylene is having sp hybridizations, and the sp hybridizations will be having linear symmetry. Linear symmetry. So linear symmetry, that is for the acetylene. The structure of acetylene is CH triple bonded CH. Ethene, that is also known as ethylene. That is also known as ethylene. That is C double bond C, H, 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 and H. Planar symmetry. They are having planar symmetry. When aniline is heated with glycerol, when aniline is heated with glycerol, all right, in presence of sulfuric acid and nitrobenzene, it gets converted into quinoline. The reaction is termed as, this reaction is scrap reaction. This is also known as scrap reaction. So when aniline is reacted with glycerol and nitrobenzoic acid in presence of H2SO4, it gets converted into quinoline, and this reaction is known as a scrap synthesis. The synthesis reaction for the quinoline is like Dobner-Miller, Friedlander, and scrap synthesis. All right, so these three reactions is related to the synthesis of quinoline, and yes, here we are having scrap synthesis. D will be the correct answer. D is the right answer for this question. Disproportionation of an aldehyde lacking alpha hydrogen in presence of an alkoxide to give esters. So we are having an aldehyde that is not having any kind of alpha hydrogens. Not having any kind of alpha hydrogen. So let's suppose we are having HCHO. 2 moles of HCSO get reacted in presence of aluminum ethoxide. Aluminum ethoxide. Okay, aluminum ethoxide, and gets converted into esters. Gets converted into ester. This reaction is known as. So this reaction is like conversion of an aldehyde that is having alpha hydrogens or do not having alpha hydrogens directly to their esters derivatives. This reaction is known as Tysenko's reaction. Tysenko's reaction. Same like the reaction between aldehydes that do not have any kind of alpha hydrogen in presence of NaOH, a base, they gives alcohol as well as acids. Alcohol as well as acids. That is oxidized as well as reduced forms of that particular aldehydes. This is Cannizzaro reaction. If we convert that particular aldehyde that are having alpha hydrogens or do not having alpha hydrogens directly to their ester derivative, that is known as Tysenko's reaction. Tysenko's reaction. So yes, this is Tysenko's reaction. Here C is the right answer. C is the right answer. We are having aluminum ethoxides. Aluminum ethoxides. Williamson synthesis is a method of preparation of ethers involve the mechanism. So the Williamson synthesis, like when we react RONA, that is also known as sodium alkoxide. This sodium alkoxide when reacts with the alkyl halide. This is your nucleophilic reagent. This nucleophile reacts, attack to this particular carbon with the leaving group halide, and we are having the formation of RO and R, and this is our ether. This is SN2 reaction, substitution reaction, in which the nucleophile attacked to this particular alkyl halide from the backside of your leaving group. This is SN2 reaction. It's a one-step reaction. One-step reaction. SN2 reaction. It will be the right answer. SN2 reaction. Pyridine on heating with it, nitrating mixture gives. So pyridine, that is, pyridine do not give any kind of electrophilic substitution reaction on the lower temperatures, at the room temperature. So for the nitrating mixture, that is HNO3 plus H2SO4. This is possible only and only when the temperature exceeds 300 degrees centigrade. So at higher temperatures only, this pyridine ring can undergo electrophilic substitution reaction only at the third position or fifth position. If the third is blocked, then fifth position is possible. So at 3 or 5th position, no 1, no 2, no 4. It's only third position where electrophilic substitution reactions, ESR, can happen in the pyridine ring. So you see, that is 3-nitropyridine can be the right answer, but this reaction is possible only and only at the higher temperatures. Higher temperatures. Hinsberg synthesis is related to the, so Hinsberg test is related to the identification of amines, 1 degree, 2 degree or 3 degree amines, while the Hinsberg synthesis reaction is related to the formation of thiophene. So yes, we are having here D, like Hinsberg synthesis is related to the thiophene, while the Hinsberg test is related to the amines, in which we use benzene sulfonyl chloride, and so for the formation of sulfonamides, the 1 degree amine gets converted into the sulfonamides. Now next question we are having, when the aldol product is heated with a strong base, then it reverts back to the equilibrium mixture, which mainly contains initial reactant. So basically we are having CH3, C double bond OH, 2 moles of this compound, and at the basic medium, in the presence of base, we are having R, CH3, CH3, C double bond, CH double bond, CH2, alpha beta unsaturated carbonyl compounds. Okay, this is our aldol condensation reaction. It's the reversible reaction. When the temperature is high, the reaction is shifted towards the backward. The reaction gets shifted towards the backwards, and the initial reactants are seen. The reaction is having the initial, mainly concentration is of the initial reactant, that is of this one. So this reaction is basically, this reaction is a aldol reaction. But when the reversible, like the reversible reaction where the initial concentration of your reactants is greater, it's a retro-aldol reaction. It's the reversible aldol, that is a retro-aldol. It's a reversible aldol, that is retro-aldol concentration, retro-aldol reaction. Which conformer of cyclohexane is chiral? Alright, again we are having the same question. Cyclohexane, that is chiral. So yes, it's a twist boat. It's a twist boat. So yes, C is the right answer. Following reaction is, we are having alkene when it gets hydrogenated to give alkane. This is only possible in nickel, platinum, palladium, rhodium, in these kind of catalyst, in these kind of catalytic metals. So this is all about Sabatier-Sonnendrens reaction. This is all about Sabatier-Sonnendrens reaction, where the hydrogenation is taking place on the pi bonded systems of the carbon in the presence of nickel, platinum, palladium, these kind of catalytic metals. So yes, D is the right answer. Name the following reaction. We are having a sodium liquid ammonia. So when alkyne is treated with sodium or lithium metal in liquid ammonia, it gets addition of hydrogens. The alkyne gets addition of hydrogen on the trans fashion. Both the hydrogen atoms, basically, if one of the carbon is getting added hydrogen in this direction, so this one will be having addition of from the this side. Or if this is getting addition of hydrogen from this position, so this carbon will be having addition of hydrogen from this position. So this is a trans addition of hydrogen. It's known as Birth reduction. That is also known as Birth reduction. If we use platinum poisoned with barium sulfate, like You can also see like if we are using Lindlar catalyst, then only the addition of these hydrogens could be seen in a cis fashion, like both the hydrogens adds to this pi bonded carbons in a cis manner, but in the case of sodium or lithium metal in liquid ammonia, it gets addition from the trans manner, and this is known as Birch reduction reaction. 2-butyne and 1,3-butadiene. So basically we are having 2-butyne and 1,3-butadiene. So this is all about what kind of isomerism? Chain isomerism? No, not at all possible. Basically we are having alkyne functional group present in this structure, and in this we are having alkene functional group. So this is all about functional group isomerism. There is change in functional group. So yes, the both structures are having functional group isomerisms. In Victor-Meyer test, all are true except in Victor-Meyer test. Like the Victor-Meyer test is related to the identification of 1 degree, 2 degree and 3 degree alcohols. The RBC, you can simply learn this test by RBC. That is, when 1 degree alcohol reacts in the Victor-Meyer test, it gives red blood color. Blood red color or red blood color. Okay, when the 2 degree alcohol, this is for the 1 degree, this is for the 2 degree and this is for the 3 degree. When the 3 degree, when 2 degree alcohol reacts in the Victor-Meyer test, it gives RB, that is blue color. And the 3 degree is having colorless. It gives colorless. 1 degree, 2 degree and 3 degree, RBC in the Victor-Meyer test. So 1 degree gives blood red color, alright, correct. 2 degree blue color, correct. 3 degree no color, okay, colorless. 3 degree green color, no. We are having RBC, so D is incorrect. Except, all are true except. So D is not correct, not true. When phenyl methyl ether reacts with HI, we are having phenyl methyl ether reacts with HI, we are getting, so OH and I, alright. So this is having, oxygen is having lone pairs and delta plus, delta minus. This attracts with this one, OH, CH3 positive, now iodine minus this, and attracts to the CH3 to give, and we can see we are having the formation of phenol plus CH3 iodine. So we are having phenol and methyl iodide. There is no methyl iodide mentioned here, but yes, the phenol is mentioned. So yes, D is the right answer. We will be getting phenol. Phenol, when it first reacts with the concentrated sulfuric acid and then with the concentrated nitric acid. So we are having phenol in the presence of concentrated H2SO4 and HNO3 nitric acid. This basically gives you NO2 electrophile. That is a nitrating mixture. It's a nitro electrophile that gives nitration on the phenol. So phenol is ortho para directing group. So this electrophile NO2 will be basically adding either to the ortho or para positions. So we will be getting ortho or para position, but both the options are here. Which will be the right answer? So for the case of ortho, look, we are having ortho. You can see that there is intramolecular hydrogen bonding in the case of orthonitrophenol. So whenever there is formation of hydrogen bonding, the intramolecular hydrogen bonding, that particular compound is more stabilized. So the formation of orthonitrophenol will be the major quantity, and in organic we always discuss about the major products. So the orthonitrophenol will be the major amount. So that's why it will be your right answer. Which of the following is an electron deficient molecule? Which will be the electron deficient molecule? Look at this BH3, like a boron. Only 3 hydrogens. There is a vacant p orbital on the boron. Since it's just having 6 electron system, there is no electron on its 3p orbital. that is left unhybridized. So this BH3, BF3, AlCl3, these all are having Lewis acid structures. They are basically having electron deficiencies. So yes, B will be the right answer, BH3. Which one of the following is chiral? Which will be the chiral one? 1,1-dibromo, 1-chloro. Since there is 1,1-dibromo, not at all possible. 1,3-dibromo, 1-chloro, propane, okay. 1,3-dibromo, okay, it could be correct, I guess. The bromine is present on the 1 and 3 position, and the chlorine is present on the first position. All right, so 1-bromo, 1-chloro, so there is 1 hydrogen here, and CH2, 3-bromo. So we are having 1 chiral carbon, the first chiral carbon. All right, so this can be chiral. Okay, 1,1-dibromo, again there is 2 bromine on the same carbon, not at all possible. 1,3-dibromo, 2-chloropropane, there is a 2-chloro and a 1,3-dibromo, that is again a non-chiral system. Okay, so yes, B will be the right answer. B will be the right answer. Okay, B will be the right answer. Ketone on reduction gives, so ketone on reduction gives, ketone will be giving 2-degree alcohols. So the formaldehyde, it will be giving, formaldehyde will be giving you 1-degree alcohol, 1-degree alcohol. The aldehyde, this aldehyde, and gives you 1-degree alcohol. This ketone will be giving you 2-degree alcohol. 2-degree alcohol. All right. So the ketone will be giving you 2-degree alcohol. That is also known as secondary alcohol. So B is the right answer. Propanone and 2-hydroxypropenes are, yes, they are tautomers. Propanone, that is having keto form, and the 2-hydroxypropene, that is having alkene and ol. So enol form. Keto enol form, yes, they are tautomers. They are tautomers of each other. Pinacol, pinacolone rearrangement, the final product is ketone. What is the starting compound for the rearrangement? What was the starting compound? That was 1,1-diol, 1,2-diol, that is also known as vicinal diol. This was your starting compound. Since the reaction is all about pinacol, pinacolone. So the pinacol, this is the pinacol structure. This is the structure of pinacol. So the pinacol and pinacolone rearrangement, during the pinacol and pinacolone rearrangement, we are having the dehydration of the OH groups to produce that particular desired pinacolone. So this is 1,2-diol, that is also known as vicinal diol. Vicinal diol, there is no such vicinal diol. So yes, 1,2-diol. So the B is the right answer. B will be the correct answer, that is 1,2-diol. Test is used for the distinction of primary, secondary and tertiary amines done by. So the 1-degree, 2-degree and 3-degree amines, the distinguish between these amines can be only possible because of the benzene sulfonyl chloride, that is also known as Hinsberg test. The 1-degree amine will be showing you the fastest sulfonamides. The 2-degree also showing you the formation of sulfonamides, but the 3-degree there is no such possibility for the sulfonamides. So yes, it's all about the amines distinguishing can be done by the Hinsberg test. Yes, D is the right answer. D is the right answer. And epoxy ring can be prepared by epoxy ring, that is also known as when the alpha haloesters reduced gets reacted with the carbonyl compounds, they gives you alpha beta epoxy ring. So this is all about Dargen's glycidic ester synthesis. Dargen's glycidic ester synthesis. Alpha haloesters when it reacts with the carbonyl compounds. 3D structures can be represented on 2D paper by Newman projection. All right, correct. It's all about the Newman projection. Sohor's projection, okay. This is like Sohor's projections and the Fisher projection. This is all about Fisher projection. All of these projections are useful for the representation of the carbons in a paper. That is, a 3D structure in a 2D paper is possible by these 3 conformations. Next question we are having, COOH group is considered as, the carboxylic group is considered as electron withdrawing group, donating group, repulsive, not at all possible. It's electron withdrawing group, carboxyl, that is having strong -I group. Stephen's reduction reaction is used for the preparation of, so the Stephen's reduction, that is RCN. When this RCN is treated with SnCl2HCl, it gets converted into RC double bond OH, that is aldehyde. That is aldehyde. So this is used for the production of formation of synthesis of aldehydes by the reduction of nitriles, alkyl nitriles in presence of SnCl2 and HCl. So yes, aldehyde will be the right answer. Most stable carbocation among the following is most stable carbocation: trialkyl carbocation, benzyl carbocation, tropylium carbocation, or triphenyl carbocation. The tropylium is the most stable among all the given structures. After tropylium, it could be triphenyl, 3-phenyl carbocation, that is also a triphenyl methyl cation. So yes, after tropylium it could be triphenyl, but among all them, first will be the tropylium one. That is a 7-member ring with 3 pi bonds and a cation on the 7th carbon. Haloform reaction is given by the compounds except. So the haloform reaction is possible only in this kind of carbon and oxygen rearrangements. So if we are having the arrangements like this, so acetaldehyde, we are having CH3CO double bond H. Okay, so acetaldehyde is having this kind of configuration. Acetone CH3C double bond. Okay, this is also having. Methyl ketone methyl C double bond. Okay. Acetic acid. Acids do not give haloform reaction. Acids are not undergoing haloform reactions. Acid can never show haloform reactions. All are showing except, so this acid, that is acetic acid, can never show haloform reactions. Acids can never show haloform reactions. Given a compound shows which type of isomerism, we are having benzene ring directly attached to S double bond O and cyclohexane ring. While this cyclohexane is attached with the sulfur, here benzene was attached to the sulfur, here cyclohexane is attached to the sulfur group. So this is all about metamerism. With respect to this SO3 group, there is a change in alkyl group, or you can say that there is change in the carbon skeleton on the both the sides, left side and the right sides. So these two structures are basically metamers of each other. They are metamers. They are metamerism. They are showing metamerism. So yes, D is the right answer. D will be the correct answer. That is metamerism. Okay. Bayer's reagent, that is cold diluted alkaline potassium permanganate solution. 1% cold alkaline diluted solution of potassium permanganate is also known as Bayer's reagent. This Bayer's reagent basically shows addition reaction on the alkenes, the syn additions of OH. So we are having alkaline, acidic, neutral, aqueous. This is alkaline chemophore. 1% cold diluted alkaline solution of potassium permanganate, that is also known as Bayer's reagent. So yes, A is the correct answer for this question. Bayer's reagent. Name the following reaction we are having. Aryl iodide. So benzene with iodine group attached, we are having with the copper, and again we are having aryl iodide. So this aryl iodide in presence of copper metal in a sealed tube gets condensed, gets fused to give biaryl compounds, and this reaction, when we use copper atom, this is about Ullmann's reaction. If we are using sodium metal, this reaction will be Wood's reaction, and if we use zinc metal, this reaction is all about the Franklin reaction. So just changing the metal, the name of reaction changes. So this will be a Ullmann reaction. It's a coupling reaction, that is Ullmann reaction. Okay. Dobner-Miller synthesis, double door fridge, that is the Dobner-Miller synthesis, the Friedlander synthesis, and the Bissler-Napierski synthesis. All these three synthesis reactions are like they are used for the production, they are used for the synthesis of isoquinoline. They are used for the synthesis of isoquinoline. Isoquinoline, no pyrazole, no imidazole, no quinoline, and thiazole. All right. Dobner-Miller, oh my bad. Dobner-Miller, Friedlander, my bad. Dobner-Miller, Friedlander, Dobner-Miller, Friedlander, and scrap. These are synthesis reactions for the quinoline. They are used for the synthesis of quinolines. While for the isoquinoline, we use pictet, we use pictet gams, we use Pomerange frutis, and we use Bissler-Napier-Lusky ski synthesis. These three reactions are used for the synthesis of isoquinoline. So this Dobner-Miller, that will be used for the quinoline synthesis. Quinoline synthesis. Okay. Moving to the next question. Product obtained by benzene and succinic anhydride by Haworth synthesis. So benzene, when reacts with succinic anhydride, okay, succinic anhydride, it gets converted into naphthalene. It gets converted into naphthalene, and this is the reaction for the production of naphthalene. This is Haworth synthesis reaction. Haworth synthesis reaction. Cinnamic acid shows the following type of isomerism. Cinnamic acid, COOH H. So basically this is having restricted rotation around these two double bonded carbon atoms. So we are having a trope isomerism is related to the biphenyls. The biphenyl system with the ortho heavier substitutions, heavy group substitutions at the ortho position, they show a trope isomerism. Conformation is about the single bonded atoms like alkanes and cycloalkanes. Geometric, all right. So yes, this is all about the geometrical isomerism. The restricted rotation around these double bonded carbons shows the optical isomerism. So yes, C is the correct answer. Sodium phenoxide reacts with CO2. We are having sodium phenoxide. Sodium phenoxide reacts with the CO2 at 125 degrees centigrade, higher temperature, and 5 atm pressure. 5 atm pressure gets converted to salicylic acid. This is reaction. This reaction is all about Kolbe's reaction. This is all about Kolbe's reaction. So yes, C is the right answer. Balz-Schiemann reaction is the method to prepare fluorobenzene from benzene diazonium salt by first converting it to benzene diazonium salt. We are having N2 plus Cl minus. In presence of HbF4 minus, we are having N2 plus and H is gone BF4 minus. So this is all about benzene diazonium tetrafluoroborate. Benzene diazonium tetrafluoroborate. This is the intermediate which get converted into directly fluorobenzene. This is all about Balz-Schiemann reaction, the formation of fluorobenzene from diazonium salt. A is the right answer. Find the end product of the reaction. We are having benzaldehyde in presence of concentrated NaOH. We are not having any kind of alpha hydrogens with this particular carbonyl group. So in presence of NaOH, what we are going to see? Para-hydroxybenzene, benzyl alcohol, benzaldehyde, and 2-hydroxybenzoic acid. So this benzaldehyde gets converted into for COO minus Na plus and oxidized form and the reduced form, that is having CH2OH. So we are having benzyl alcohol and sodium benzoate. There is no any sodium benzoate in the option. So yes, we are having benzyl alcohol. So B is the right answer. B will be the right answer. Benzyl alcohol. The reaction is all about Cannizzaro reaction. Benzene reacts with acid anhydride in presence of AlCl3 to give aromatic ketones. This reaction is, we are having benzene reacts with acid anhydride, RC double bond OO, acid anhydride in presence of AlCl3, breaks, and the carbocation intermediate we are going to see. This carbocation attack to this benzene ring to give aromatic keto compounds, aromatic ketone compounds. This reaction is a Friedel-Crafts acylation. This reaction is all about Friedel-Crafts acylation reaction. C is the right answer. IUPAC name of the given structure is Spiro 1, 2, 3. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. 7. So 3, 7. We are having 3.7. 7,3,10 undecane. There is one spirocarbon that is not counted. So yes, 3,7 undecane. Spiro 3,7 undecane. Spiro 3,7 undecane. 3,6,3,8,2,9. Not at all possible. Spiro 3,7 undecane is the right answer for this question. The correct IUPAC name of the compound is IUPAC. It's the bridged compound. Bicyclic system. We are having bridges. First, second, third, fourth, fifth. 1, 2, 3, 4, 5, 6, 7, 8. We are having 8 carbons, so octane. All right. So 2 options will get eliminated. We are having 1, 2, 3, 4. 1, 2, 4, 2, 0, 4, 2, 0. Bicyclo 420 octane. It's bicyclo 420 octane. A is the right answer. Deoxygenation of aldehydes and ketones to hydrocarbons. We are having carbonyl compounds. It could be aldehyde or ketones. The deoxygenation and gets converted into hydrocarbon. That is, we are having CH, hydrocarbon. It's carbylamine. Carbylamine is not possible. This is for the 1 degree amines. Okay. Aldol condensation, no. Crossed aldol, no. It's all about Wolff-Kishner reduction. It could be either Clemmensen reduction reaction or Wolff-Kishner reduction reaction. If we treat this compound with NH2 in a base, KOH, let's put it down, KOH. So this compound, this carbonyl group gets reduced to hydrocarbon. So yes, A, that is Wolff-Kishner reduction, will be the right answer. And the reaction sodium alkoxide with alkyl halide. Sodium alkoxide, RO minus Na. Sodium alkoxide with alkyl halide, let's suppose RCl, gives ether and sodium halide. This is called, so this reaction ROR and NaCl. This reaction is known as, this is Williamson ether synthesis. This is all about Williamson ether synthesis. Williamson ether synthesis reaction. So C is the right answer. Williamson ether synthesis reaction. So C is the right answer. This is all about today's pharmaceutical chemistry class. I hope you all enjoyed the session. Make sure you practice these kind of questions for these upcoming NIPER examinations. The questions level for the NIPER examination is like there is not that much higher level. You simply have to fight with the time. So thank you all. We will be joining with you again in some other sessions. Thank you. Thank you everyone.